Okay, welcome back. So today we are going to start with some element from section 13.5, and then we can work our way back to 13.4. So we're going a little bit out of order, but I think this is a good ordering for kind of detailing our first major theorem for today. So we're going to cover something called divergence. So what we're going to do is consider a vector field in R3 defined by its component functions P, Q, and R. We define the divergence of this vector field F as can write the divergence of F is equal to partial P partial X plus partial Q partial Y plus partial R partial Z. So each component function is taken with a derivative with respect to that element. So this is the X component, Y component, and Z component, and then we add all of these things together. We can rewrite this if we observe that if we look at this gradient operator, that we've been using before, was some vector of these differential operators. Then what we could do is say that the divergence of F is the dot product between this operator here and our vector field F. Most of the time, you don't really see divergence written out this way. You see it written like this right-hand side. This typically means the divergence. So in the book or in elsewhere, most of the time you'll see this written as for the divergence of F. So it is the dot product of the vector field with this differential operator here. So in the context of fluid flow, the divergence represents this net rate of change of the mass of fluid flowing from one point per unit volume. So if you had some point in space and you wanted to know how much mass is flowing from that point, you would calculate this divergence, right? It kind of tells you how much is coming out of that location, right? It's the divergence of that thing. So in the context of fluid flow, if the divergence measures the tendency of fluid to diverge from a point, and we have that the divergence of F is 0, then we say F is incompressible. So this isn't really a fluids class, so we won't kind of go into it, but yeah, divergence shows up for fluid flow, right? It's how much is kind of leaving this point. So now, consider the gradient of a scalar function f. So we take our gradient, we know this is partial f, partial x, partial f, partial y, and partial f, partial z. The divergence of the gradient of f here so we're taking the divergence of the gradient of f. Now it might be a good time to kind of note that the divergence acts on a vector, whereas the gradient acts on a scalar, right? So gradient acts on a scalar function, but the divergence acts on a vector function. So once we take the gradient of a scalar function, we get a vector function, and then therefore we can take the divergence of it. So we can also write this as the other definition using our dot product here. So this is partial x, partial y, partial z, dotted with our partial f, partial x, our partial f, partial y, and partial f, partial z. In other words, we could write this as the second derivative of each dimension. So we have x, y, and z all added together. This operator shows up a lot. So we introduce, we're not going to talk about it too much in this class, but in physics, wave flow, this comes up very, very often. So we introduce the operator this thing squared basically means we're taking the dot product with itself. You might find this funny, but the shorthand way of writing this is just delta, so upside down. So this is called the Laplacian. So the Laplacian of f these are all the ways that we can write it. And in R3, this ends up just being the sum of each of our second derivatives with respect to x, y, and z. You might remember Laplace equation from back when we were looking at partial differential equations to see if things would be satisfied. Laplace equation, for instance, in R2, or I guess we can even do R3, was this. This is Laplace's equation in R3. Or we could just write it as that. And that's why in a Laplacian. Okay. So let's do some examples. First, let's find the divergence of the vector function x squared minus y, xy minus y squared. So we can write this as, this is actually called del, so we can say del dot f. So remember, this is partial x, and since we're in R2, it only goes up to partial y, and we're dotting it with x squared minus y, xy minus y squared. Oh, there's a question about scrolling up about here. Okay. And then now we have here, we need to do the partial derivatives. So we do partial x on x squared minus y plus partial y of xy minus y squared. So this gives us a 2x here, and then we have plus x minus 2y. So in total, we get 3x minus 2y. Okay, let's do one last example, and then we can move on to our big theorem. So let's see, does the function sine of x e to y solve the Laplace equation? So let's go ahead and take the Laplacian of this. So we're taking the Laplacian of f, which is del dot the gradient of f. So let's go ahead and take the gradient first. So this del dot, and our gradient here, so we take an x derivative, we get cosine of x e to the y. And then we take a y derivative, we get sine of x e to the y. So then we take the divergence of this new vector function. So that means we take an x derivative of this, which gives us negative sine of x e to the y, plus we take a y derivative of this, we get sine of x e to the y. And of course, these two things cancel. They're just negatives of one another. So it ends up looking like this function does satisfy the Laplace equation, that the Laplacian of f is equal to 0. Okay, so divergence is actually pretty easy, right? You're just taking x derivatives, y derivatives, z derivatives, and so on, and then just adding those all up. Just like a normal dot product with a few extra steps, right? Just taking some derivatives. So now let's take a side step to kind of talk about this theorem. And then later on, once we establish a theorem, we're actually going to have to use this divergence to spice it up a little bit. So here, let's talk about Green's theorem. So this is our first big powerful theorem for this chapter. So imagine some closed curve in R2 that encloses some region. So we're in the XY plane here. And we have some curve, maybe something like this. It has this orientation. We'll call this curve C, and it encloses some area that we'll call D. We define some functions P and Q, both functions of X and Y, along C and in D as two differentiable functions. So somewhere in C and D, we have these differentiable functions P and Q. If D is some simple region, so we're going to do a proof of this theorem that involves just using a simple region, but it's a little bit more powerful than that. But for the context of the proof, let's look at just a simple region here. That if D can be written as the set of all points X and Y such that we have that X is bounded by A and B, and then we have that Y is bounded between two functions of X, G1 and G2. Or we could do vice versa. But let's stick with, maybe we could write it like this. It works the other way as well. So let's do a quick sketch of what's going on here. Maybe our domain D, let's do some straight lines. Here, here. And then maybe we have some lower portion here. And we have maybe some upper portion here. We're going from A to B, and then we have G1 and G2. This is our domain D. So what I'm going to do is I'm going to break up our region into a C1, C2, C3, and C4. So our parameterization of our curve goes like something like that. If this is true, then the area integral over the region D of partial P, partial Y, dA, what we're going to do is let's actually try to do out this area integral as far as we can. This is the integral from A to B of G1 of X to G2 of X, partial P, partial Y, dy, dx. Now we're taking a y partial derivative, but our first integration is with respect to y. So all we end up with is this is equal to the integral from A to B of P of X, G2 of X minus P of X and G1 of X dx. So we've integrated out the y's, and everywhere there was a y from the fundamental theorem of calculus, we put G1 or G2. So this is our resulting integral here. Now we can't really integrate this too much further, but what we will do is we now look at the line integral over the curve C of P x and y dx. So we let x is equal to x. So our parameterization, we're not doing respect to t here or ds. We have just a dx, and y is equal to G1 of X along the C1 segment, right? So remember our C1 segment from up here is just this bottom curve, right? So y is equal to G1 of X along that. X is equal to X and y is equal to G2 of X along C3, right? So we look up here, and on C3, we have a definition for y. It's just this G2 function. On the C2 and C4, these are just straight vertical lines at x is equal to a and x is equal to b. So dx is actually 0 here. There's no change in x along this segment. So the line integrals there are 0. And we'll say more about that in just a second. So then the line integral along C1 of P of x, y dx is equal to the integral from a to b of P of x, G1 of x dx. And the line integral on C3 of P of x, y dx, this is the integral from a to b of p of x g2 of x dx. So now the line integral on C2 and the line integral on C4 are both equal to 0. Since on those line segments, there is no change in x, since dx is equal to 0 here. So the only portions that contribute to the full line integral are C1 and C3. Thus, we have that the total line integral of p of x and y dx is equal to the line integral over C1 of p dx plus the line integral over C3 of p dx, or in other words, this is the integral from a to b of p of x g1 of x minus p of x g2 of x dx. Oh, sorry. The reason why that's negative, I should correct this right here. This doesn't go from A to B, this goes from B to A. Sorry about that. That goes from B to A. Because given our plot above, we're going in this orientation. So we can start from B and we go up to A. Or we could write this as negative A to B of P of X G2 of X dx. There we go. Sorry about that. So that's why this is a minus here. But this looks awfully familiar to that double integral, right? If I scroll all the way back up here, this double integral that we wrote was exactly this. We had p with g2 subdiv minus p with g1 subdiv. Here's the same thing. So it looks like the line integral over c of the function p of x and y dx was equal to, there's a difference between this one and the one above, is that now this is g1 minus the one with g2 subbed in, so there's actually a negative. So we have minus the area integral over d of partial p partial y dA. So you can actually go through this proof using the Q function. So in a similar fashion, we have that the line integral over C of Q of x and y dy is equal to the positive area integral over d of partial q partial x dA. So this brings us to Green's theorem. Is that the line integral of P dx plus Q dy is equal to the area integral of d over d of partial q partial x minus partial p partial y dA. This is really powerful. This tells us translations between the curve C and the region D. So we have a line integral on the perimeter of D, and that could be equated to the area integral over the region D. And this is pretty powerful. So let's say, this line integral is pretty hard to calculate. This area integral might be very simple, right? Instead of doing a parameterization of this line, we could just look at the area integral of the thing that it encloses. But we're not going to stop here. So this is Green's theorem, and now we're going to try to adapt this a little bit. So now, imagine we have some vector field. That has component functions P and Q. If we define the path of C via our parameterization R of T, where T goes between A and B, then the unit tangent vector is equal to x prime over T, the magnitude of R prime of T, y prime of T over the magnitude of R prime of T. So this points in the direction of C at any time T. We can find the normal vector pointing away from D as, and I'll write this down and then we'll do a little proof for it. This is 1 over the magnitude of r prime y prime of t negative x prime of t. So what is this normal vector? Let's do a quick sketch here. If I have some region and I've got some path. So the unit tangent vector is always pointing along this path in the direction that we're traveling in. This is our region D. It might be of interest for us to find out at any given point what is the normal to this curve that is pointing away from the region D. So the unit tangent vector will be at a 90-degree angle with this normal. So how do we find that thing? Well, what we're going to do is kind of try to bring the shape into R3. We know what the unit tangent vector is. We can find it. And we also know that a vector that points out of the screen is perpendicular with these other two. And then to find this last thing, we can do a cross product. So if we look at the unit tangent vector, which was given by r prime over the magnitude of r, so x prime over the magnitude of r prime, and then y prime over the magnitude of r prime. And we cross this with a vector, oh, sorry, there's also should be a 0 here. And we cross this with 0, 0, 1, something that points outside, that points out of the screen here. So this gives us our I, J, K, x prime over magnitude of r prime, y prime over r prime, 0, 0, 0, 1. So the x component of this guy is this times this. So we get a y prime over the magnitude of r prime. The j component, remember we have to take a negative, so we get minus x prime over the magnitude of r prime. And finally, the z component is just going to end up being 0, which makes sense, right? There's no z component to this thing. And that gives us the vector that we were looking at before, this thing right here. So in R2, we can always just write this very generally, that the normal vector is 1 over the magnitude of r prime times the vector y prime, and then minus x prime. Okay, so then why are we even looking at this normal? Well, once we have this normal defined, let's take a look at the line integral of c f dot n ds. So remember when we were talking about line integrals, I said that eventually we had flow integrals and then we were going to have flux integrals, right? This is the sum of all of the vector function f that is pointed out of this curve here, right? We're accumulating all of the components of f that are pointing in the normal direction and adding all of those up. So what we can do a parameterization. So this is just a normal line integral. So a to b, our integrand is f dot n, and our ds becomes r prime of t dt. So remember that we said that f was had component functions p and q. Well, let's go ahead and do out this normal or this dot product here. This is the integral from a to b of p of x and t and y of t times y prime of t over the magnitude of r prime of t minus q of x of t y of t times x prime of t divided by the magnitude of r prime of t. And then this got multiplied by this thing right here, which is just the magnitude of r prime of t dt. So obviously these magnitudes of r prime cancel, and we're left with the integral from a to b of p of x of t y of t y prime of t minus q of x of t y of t x prime of t dt. So let's look at these y primes and x primes, because now we have, this is a dx dt, and I have a dt here, and this is a dy dt times this dt here. So rather than write this as a parametric version of the line integral, we can rewrite this back in its original form as a line integral over the curve C of p dy, since we've got a y prime here, minus q dx. So what we did was we started with just this vector here. Sorry, not this vector, this line integral here. Right, and all we did was just a dot product. This is just a line integral, f dot n, the normal, ds. And I converted this to a line integral with respect to dy and dx. So these are equivalent. We could just write these in either way. But the cool part about this expression here is that it looks remarkably similar all the way back up here to our Green's theorem expression, except this just had a plus, whereas the thing that we have below has a minus, and we'll notice the component functions are switched. So would this be how we define flux with that last integral? Yeah, so this is a flux integral. Yeah, flux line integral. So if you wanted to calculate the flux through a curve, this is the way to compute it. So now, what we can do is use Green's theorem on this expression here. So by Green's theorem, we can say that this is equal to the double integral over the region D of partial p partial x plus partial q partial y dA. Well, the integrand on this looks awfully similar to the divergence. So another way to write this is that this is the area integral over the region D. The divergence of f dA. So to kind of wrap up our thoughts here, we have our closed line integral over C, and we have f dot n ds. This is the integral, the double integral over d of the divergence of f dA. So here, this is, the book kind of talks about these as different cases, like Green's theorem for flow and Green's theorem for flux. Green's theorem really is just this expression that we've defined up here. But we were able to utilize Green's theorem for a flux integral. So these are very circumstantial, right? So the one up all the way up here is typically called the flow version of Green's theorem. And the one down here is typically the flux version, although they more or less come from the same idea of how we translate a line integral to an area integral. Okay. So let's do some examples. How do we know which version to use? I hate using that word because, you know, to me, they're not different versions. They're just the same concept applied to different line integrals. But let's kind of figure out when to use these concepts. So let's do some examples here. We're going to find the line integral. So this is a closed line integral of x times y dx plus x squared y cubed dy where C is the triangle that's created by 0, 0, 1, 0, and 1, 2 that has a counterclockwise orientation. Okay, first thing to do, let's sketch out our triangle. So we go from the origin. We also include 1, 0. Something like that. And then we go up to 1, 2. And then we also come back down to the origin. So this is our triangle here. So before we talk about doing any kind of parameterization, we're just going to sketch out what this region looks like. So we have 0, 0, 1, 0, and 1, 2. So it might be worthwhile to solve for the equation of this hypotenuse. It's just y is equal to 2x. And we have, this is our region C. Now we could do brute force the line integral on each of these segments, right? I could say this is C1, I can say this is C2, and this is C3, and then I can calculate the line integral for each of those segments and then add them up. Or what I could do is use Green's theorem. Rather than do the line integral, I can take a look at the area integral of the region D here. So from my line integral, I can deduce that P of x and y is equal to x times y, and q of x times y is equal to x squared y cubed. So remember, our Green's theorem said that we can convert the line integral of c of x times y dx plus x squared y cubed dy as the area integral over the region D, where I had partial x of x squared y cubed, and then I'm subtracting partial y of x times y dA. So this is utilizing Green's theorem. We have a p and a q, and we have partial q, partial x minus partial p, partial y. Right, so this is just utilizing Green's theorem. So instead of doing the line integral on each of these small segments, I can just look at the area integral of the region D. And it's a triangle, right? The area integral shouldn't be too bad. So we go ahead. So let's figure out the integrand first. This looks, we take an x integral here. We get a 2x times a y cubed. And then we're subtracting the y derivative here. So this is just minus x. Let's do dy dx as our integration order. That means we go from 0 to 2x and 0 to 1 for x. So all I need to do is this area integral. This is the integral from 0 to 1. 1/2 x y to the 4th minus x times y, evaluated at y is equal to 0 and y is equal to 2x dx. This is the integral from 0 to 1 of 8x to the 5th minus 2x squared dx, or 4/3 x cubed, or sorry, the 6th minus 2/3 x cubed, evaluated at x equals 0 and x equals 1. This ends up giving us 2/3. So the area integral, which was much simpler than trying to do the line integral on each of these segments here. Now, Green's theorem only works for enclosed regions. So, if you have an area integral, or sorry, you have a line integral that doesn't enclose a region, you can't apply Green's theorem to it. But in this case, we have a closed line integral, and it encloses this region D. And via Green's theorem, we can rewrite this line integral in terms of a double integral over the region D that the line encloses. Okay, with that, why don't we take our 5-minute break here, and then we can come right back. So go ahead, get some water, go use the restroom if you need to, and we'll be right back. Okay, so let's continue. So let's do another example. I think I have lined up that we're doing. We're going to verify Green's theorem for the flux of the vector field x minus y, comma x for the region bounded by the unit circle. Okay. So this means if we want to verify, what we're going to do is we're not actually going to enact Green's theorem, but we are going to calculate the line integral as well as the area integral. So we're going to both calculate the left-hand side and the right-hand side of Green's theorem and make sure that they're the same thing, right? Green's theorem says that they're equal, so let's kind of verify that they are in fact equal. So let's start with the line integral. So in order to do the line integral, you should always think parameterization. Line integral, parameterization. So I think about the curve C that loops around this unit circle, and I want to parameterize that. A lot of ways to do this, but what I'm going to choose is a cosine of t and a sine of t. And I'm going to have t run from 0 to 2 pi. It's perfectly natural parameterization for the unit circle. So in order to calculate this line integral, I'm going to need r prime. This is negative sine of t. And cosine of t. Which means that the magnitude of r prime of t is the square root of sine squared of t plus cosine squared of t. That's just equal to 1. We have a sine squared plus a cosine squared. It's pretty nice. Okay, so this is trying to calculate the flux, right? How much is going through this curve C, right? So that means we need the normal vector, which we found in R2, that this is always the case. We have that it's 1 over r prime in magnitude times the vector y prime and negative x prime. So we go ahead and substitute those in. Well, our magnitude is just 1. That's nice. And then y prime was just this cosine of t. And then negative x prime is just sine of t. Funny enough, this is r of t. And just a simple sketch will kind of prove why that's true. For a circle, little cool feature. If I have a circle here and I wanted to know the vector that's normal to the surface that is pointing outward, well, the vector that points all the way out to the origin, to that line, is the same direction as that normal. And because it's a unit circle, it has a unit length, which is what this normal vector should have. It should also be a unit vector. So it makes sense that we end up with just r of t here. It is the vector that is normal to that surface, to that curve right there that's pointed outside. So if we need to keep calculating this flux, what we need to do is look at f dot n. So this is x minus y, comma x, dotted with cosine of t and sine of t. So we have here x's and y's, but we will need to translate those to their corresponding for our parameter choice, right? So we said that x was equal to cosine of t. We said that y was equal to sine of t. So we can go ahead, plug that in before we do this dot product. So this is cosine of t minus sine of t, comma, cosine of t, dotted with cosine of t, sine of t, or cosine squared of t minus sine of t cosine of t plus cosine of t times sine of t. So these two terms right here end up canceling. They're just negatives of one another. So we get cosine squared of t. So that's our integrand. So we're looking at the line integral of f dot n ds. This is the thing that we want to calculate. We did our parameterization choice from 0 to 2 pi. We found out what f dot n was. This was just a cosine squared of t. The ds to dt conversion needs an r prime in magnitude. Well, that was just a 1. And then we have a dt. So if I wanted to do the integral of cosine squared, I can use a double angle formula to help me out here. So this is the integral from 0 to 2 pi. 1 plus cosine of 2t over 2 dt. That's just using a double angle formula. So this is t over 2 plus sine of 2t over 4 evaluated at 0 and 2 pi. This ends up just giving us pi. So just to kind of reiterate here, we're not using Green's theorem to actually do the problem. What we're doing is verifying that it works via calculating the left-hand side and the right-hand side independently. So this was the line integral. We found the flux through this interface, this curve C. But now let's go ahead and do the area integral. Do we still get pi for this? So to do the area integral, remember we have f dot n ds here. We showed that if we have this line integral, the area integral that we need to compute is over the region D of the divergence of f dA. So this is the integral that we're trying to calculate. The first thing I'm going to do is actually look at the divergence of f. The divergence of f is equal to, let's put our partials in here. We're dotting this with x minus y, comma x. So we take an x derivative here, we just get 1. Then we take a y derivative there, we get 0. So it looks like our divergence is just equal to 1. It's not even a function of x and y really anymore. It's just this constant 1. So our area integral over the divergence of f is the area integral over the region D of 1 dA. So we can actually go ahead and do this double integral out. We can go into polar coordinates. That's perfectly fine. But we're engineers here, right? And I know that this thing just represents the area of D, since the integrand is 1, right? Well, the area of D, remember D is just the unit circle, so that we can just use pi r squared, or this is just equal to pi. So using a little bit of logic, this area integral was significantly easier than doing this line integral. I mean, this line integral wasn't too bad, and we kind of showed how to do this flux integral, which is important. But you can have seen that if we wanted to use Green's theorem and translate this flux integral into its counterpart using Green's, that the double integral here was significantly easier to deal with. Just shows the power of Green's theorem. Okay, with that, we're going to leave Green's theorem behind. And we're going to continue with section 13.5, where we talk about curl. So we now define another operator the curl of F. So if our vector field F can be written in terms of its component functions, P, Q, and R, then the curl of F is partial R, partial Y, minus partial Q, partial Z, I hat, plus partial P, partial Z, minus partial R, partial X, J hat, plus partial Q, partial X, minus partial P, partial Y of K hat. What is this thing? Why did divergence look so nice and then the curl looks so messy? Well, the shorthand way to write this is the cross product between this del operator and the vector field F. So where divergence is the dot product, the curl is the cross product. So if we look at the cross product of F, I can write this as I hat, J hat, and K hat. We have our partials from the del operator, and then we have P, Q, and R. Well, our X component, we go ahead and we look at the determinant of this guy here. This is Ry minus Qz, matches what we have written here. And then we have negative the determinant of Rx minus Pz. So we can just write that as Pz minus Rx. matches here. And then here we have qx and py, qx minus py. Just verifying that this in fact is the curl of f. So let's do an example. Let's find the curl of f if f is equal to x, z, x, y, z, and minus y squared. Let's set up our determinant. So here we have partial y and then minus partial z of this term here. So actually, let's just do this on a brand new line, give ourselves some room. So this is equal to partial y of negative y squared minus partial z of x, y, z in the I hat direction minus partial x of minus y squared minus partial z of x times z in the j hat direction. And then plus partial x of x, y, z minus partial y of x times z. So this gives us the vector negative 2y minus xy, comma, x, and y, z. So this is the curl of our vector field. So first things first, let's talk about a theorem that involves our cross product. If a function f of x, y, and z has continuous second order partial derivatives then the curl of the gradient of a scalar function f is equal to 0. So this might not look very helpful at first, but let's kind of dive into why we can use this in the kind of mathematics that we've been looking at recently. So first, let's look at the proof. If I go ahead and take a look at the curl of the gradient of f, it's I, j, k hat. We have our del operator. And then we have fx, fy, and fz. This ends up giving us f y z minus f z y f z x minus f x z f x y minus f y x. So if all of these are continuous, we could rearrange the differentiation order, and this results in the zero vector. So I actually need to put a little vector symbol on top of this. This isn't just scalar zero, this is the vector zero. So why is this important? Like why do we really care if the curl of the gradient of f is equal to 0? Well, note, if capital F is conservative, that is to say that the vector field can be written as the gradient of a scalar function f, then the curl of that vector field is equal to the 0 vector. So that brings us to our next theorem. If f is a vector field, defined on all of R3 whose component functions have continuous partial derivatives and the curl of f is equal to 0, then f is conservative. So this gives us a way to check for if things are, it's like a vector field is conservative or not. So before, when we were talking about line integrals and we wanted to know if we could use the fundamental theorem of calculus, saying, oh, is this a conservative vector field? We looked at cases where it was true for R2, but this in general can actually, this theorem itself can actually be extended to higher dimensions as well. So as long as the curl of f is equal to 0, we know that the f is a conservative vector field, and then we can use all of that stuff that we've been talking about for path independence for line integrals. So let's do an example. So we looked at this vector field previously. We looked at the curl of it. Is this thing conservative? Well, we saw that the curl of this f was negative 2y minus xy, x, and y times z. This is not the zero vector. So no, this is not a conservative vector field. So we're going to show that this vector field is conservative and then we're going to find f such that f is equal, the vector field, capital F, is equal to the gradient of some scalar function, lowercase f. So let's look at the curl of f. All this is basically a plug and chug, so we can just look at our partial derivatives. This ends up giving us a 6x y z squared minus 6x y z squared. So we get 0 in that component. Then we get a 3y squared z squared minus a 3y squared z squared, also 0. And then a 2y z cubed minus 2y z cubed. So this ends up just giving us a zero vector. So this is in fact a conservative vector field once we look at the curl of this operator, or sorry, curl of this vector field. Now to find f, this is very similar to what we did the other day. So I'm going to write out again the vector function here, f y squared z cubed 2xy z cubed and 3xy squared z squared. And then we're trying to relate this to a scalar function's gradient. So this is fx, this is fy, and this is fz. So I know that these three things are equal. So I'm going to start with my first element here, fx. I know that this is equal to y squared z cubed, or f, which is the integral with respect to x of the first derivative with respect to x. I go ahead and take an integral of this quantity. This ends up giving me an x y squared z cubed. But I have to keep in mind that since I am integrating with respect to x, anything that's a constant with respect to x, I need to tack on here. So this is plus a function of y and z, right? Because y and z are constants with regard to x. Okay, this is now my new candidate for the function f right here. If I take this y derivative of this thing here, I can relate it to the second piece of information. So I go ahead and take a y integral. This is a 2 x y z cubed. And now this is partial y of g of y and z. So all I did was take a y derivative of this thing here. But I know that fy is equal to this thing right here. This is equal to 2xy z cubed. So notice that these two things cancel, and I'm left with that the partial derivative with respect to g, or sorry, g partial y is equal to 0. So this means that the function g of y and z, if this is a partial y derivative, any constant with respect to y will end up being 0. So this is a function of z. Okay, so the new update is that f is x, y squared, z cubed. So we're going from up here, and we know g now is a function of h, or sorry, the function h was a function of z. And now I can use that last piece of information. I can take the z derivative and relate it to the z component of my vector field f. So I go ahead and take the z derivative. I get 3x y squared z squared plus the first derivative of h is equal to 3x y squared z squared. So again, notice that these two terms cancel on both of these sides, so that I'm left with h prime of z is equal to 0. Since h is only a function of z and its derivative is 0, I know that h of z is just equal to some constant. So finally, I can say for sure that my function, my scalar function f, lowercase f, is x, y, z, is this x, y squared, z cubed plus c. Before we head out, I just want to say one thing in the context of what it physically represents, this curl. So if f represents maybe a fluid velocity field, then the curl of f details how fluid rotates around the point x, y, z. So if you have any given location and you want to know how fluid is turning around that point, that's what the curl does. And that's why it's called this curl, right? It kind of tells you how what is the rotational aspect of the fluid around the point x, y, z. If you wanted to know the speed instead of just the direction, you could look at the magnitude of the curl of f, and that will give you the speed of kind of the fluid around that given point. Okay, so then with that, we are done for today. Then we'll continue on for tomorrow. So until then, stay safe, everyone. And I will see you tomorrow.